So what type of wave is a electromagnetic wave? Also called an EM wave. Transverse. What medium does EM waves require to travel? What does the word medium mean in this context? It means substance or material. It has dual meanings. So medium has two meanings. One is middle. The other word, instead of saying material or substance, we usually say medium. But what medium or material does EM waves require to travel or exist? Yes, unlock it. You can shut it, but hold on. Mm-hmm. This is a trick question. Can light travel through empty space? So, trick question. It doesn't require a medium. They can travel in a vacuum, which is empty space. What is up? Yeah, probably a pulsar. Either a neutron star. What EM wave has the longest wavelength? The radio. What EM wave has the second highest energy? No, second highest wavelength. And uh, still wrong. Shortest. I was like, what does highest mean in this context? Sorry, I was trying to read my scribbled out handwriting from first class. So what EM wave has the second shortest wavelength? Yes. Hmm? X-ray. So the first, or the shortest, is gamma. So the second shortest will be the one right after that, which would be X-ray. Which has more energy? Microwaves or infrared? It would be infrared. Which travels faster? Radio waves or microwaves? So which travels faster, radio waves or microwaves? I'll repeat the question. Which EM wave travels faster, radio waves or microwaves? So what is the speed of an EM wave? We have a constant, the speed of light in a vacuum is 3 times 10 to the 8 meters per second. So this is true for all EM waves. So radio waves travel at 3 times 8 meters per second. Microwaves travel at 3 times 10 to the 8 meters per second. So I ask for another time. Which travels faster, radio waves or microwaves? Neither. It's a trick question. Yeah, I heard you. But I don't know if other people heard you. I don't know. I only heard you say it the last time and then I told you that. I don't know. I don't know, maybe. So, trick question. They travel at the same speed. It's due today. I'm not accepting it today if you don't turn it in as a 0. Yeah. Yeah, as long as you don't forget. So, all electromagnetic rays travel at the same speed, in a vacuum at least. And if we don't talk about what material, we assume a vacuum, meaning empty space. We assume this condition. How does microwaves differ from visible light? Or equivalently, what is the difference between a microwave and a visible light, such as green, the colors green, blue, and red? They only differ in frequency, wavelength, and energy. They have different frequencies, what are wavelengths, and energies. Other than that, they are exactly the same. It's just a limitation of our eye. It has nothing to do with the nature of microwaves and visible light. So visible light and microwaves are the exact same thing. So is radio waves and visible light, UV light and visible. The only thing they differ is what frequency uh, they're in. Everyone good? So yesterday I went over some properties of light. Say I have a piece of glass and I shined a light at it. One of three things will occur. One, according to the law of reflection, some of the light could be reflected off. It could also be absorbed. And we also know that it could travel through light, or through glass. That light can travel through glass. However, look at the path light took. It did not go in a straight line. This is known as refraction. So light can be refracted. Refraction is when light enters a new material and seemingly bends. Meaning changes direction. Here, here you can see an image of it. This is the light going into some glass, and you can see it made a change in direction. You can see light going into some glass, and you can see it changing direction. You also can see that the different colors change direction. So the color is just a wavelength. The wavelength, depending on the wavelength of light, it will change direction by a different amount. So the amount that light changes direction depends on the wavelength of light. If you have a prism, that triangle thing, and you shine white light, this is known as dispersion. Is when white light refracts or separates into its individual colors. So dispersion is when white light refracts or separates or disperses into its individual colors. Keep your mask on, Alan, and everyone. So refraction and dispersion. Dispersion is a type of refraction. Refraction occurs because light slows down in different materials. This is due to the electrons of the atoms interfering with the electromagnetic wave. Remember that EM wave, an electromagnetic wave, is a vibration in the electrical field and the magnetic field. And electrons have an electrical field, yes. Materials. Keep your mask on, Aaron. In materials, so refraction occurs more heavily when the atoms are more are packed closer together. So, for example, in air and a vacuum, so in air or vacuum are usually any gas, any thin gas. The speed of light is roughly 3 times 10 to the 8 meters per second. In water, it slows down to about 2.25 times 10 to the 8 meters per second. In glass, which is a solid, it slows down to 2 times 10 to the 8 meters per second. So generally, in gases, light travels the fastest. And in solid, light travels the slowest. And this is generally. So why does it take that turn and put your mask on? So why does it bend? Why does it actually make a turn just because it's going in a slower material? Light always tries to take the fastest path. So light will always go from one point to another, taking the path that will get it there the quickest. So imagine you have a sidewalk, 2 sidewalks, and you have mud in the middle, so concrete sidewalks. Let's say it's a wide road. What is the fastest way to go from here to here? No. Can you move really quickly through mud? Yes. This is you walking. Put your mask on, Alan. The fastest way would be trying to stay on concrete for a longer period of time. And then moving briefly through the mud and going like this. And that is exactly the same path we see light take. It moves slower in a material. Yes. This is mathematically the fastest path. I mean, you're walking. I mean, guys, trust me, this is the... Okay, quite literally, light takes the fastest path. This image right here, there is no possible way light could have taken another path that would have ended up getting here quicker. And same thing with humans. You can define it mathematically. So refraction is the reason why something like this occurs. So when you put, whenever you're looking through a material, it seems like light has been bent in whatever object you're looking through the light. So, for example, here you have a pencil in it. This image shows the true position of the pencil, but it would look like it bent like this. So if you're going bow hunting for fish, bow fishing, so you have water, this, and you have a fish, and light were to be going here, and it's going to bend like this. And if your eye was here, you would see the fish as if it was right here. So the fish is actually closer to you than what you see it at, because light refracts when it goes from one material, such as water, to air. So you want to shoot in front of where you see the fish, not where you actually think he's at, or see him at. Because again, you see at this point right here, this path, so the image of the fish will be here, but light coming off bends, so the fish is actually closer to you than it appears. You can also get images like this occurring. So the light coming from the sun is hitting his face and the sign doesn't get bended because it's all staying in air, so we see it reflect directly. However, whenever light comes and strikes the water, it's going to bend. Then it's going to hit his body and reflect off. Then it's going to hit the glass, bend some, and then it's going to go into the air and bend even more. So the true position is going to look completely different from where it's at. Again, you can have effects like this, where again, light is coming into the glass and it's bending in different directions. It's striking it and reflecting off. Oh, and here's another image. Also, I think makes it appear farther up than it really is, too. So visible light has a higher frequency than what EM wave? Which EM waves does light have visible light have a higher frequency than? Keep your mask on. So visible light has a higher frequency than radio waves, microwaves, and infrared. From high to low, what is the correct order of EM waves based on energy? So we're starting from high and going to low. So where's the highest? Gamma, then X-ray, then radio. So gamma has the highest, and this would be the lowest. This is also, and what do we call this whole group? No. What do we call the whole group? This is technically in reverse order. EM spectrum. So EM spectrum is the entire group of EM waves. So how would you order from high to low? For visible light colors. So remember, Roy G. Biv. And which one has the highest energy? So that's the highest. So we're going to start from there. Violet. And then what comes next? And blue. Alright. Divergence is a property of waves that causes them to spread out as they move. Also depends on wavelength. So if I were to shine a flashlight, is it going to go in a straight line? So it'll spread out, getting bigger and bigger and bigger. So that is divergence. Yeah, same direction. They'll spread out and get wider and wider. What would happen if I had two tiny slits in a wall? So it would go through the empty space, but now we have two waves that are spreading out. And if I have a wall here, where a crest and a crest meet, we're going to get constructive interference. So, bright spot. So constructive interference is when crest and crest meet. Where a trough and crest meet, we get deconstructive interference. Dark spot. This could also be lines. This could be dark lines. And this could be bright lines too. So we're going to end up with a series of bright spots and dark spots. And they're going to be kind of fuzzy. This is known as diffraction. Diffraction is when a wave interferes with itself, causing bright and dark patches. Now, I showed two slits. A slit, by the way, is just a hole. But this also occurs with a single slit, so this is a double slit. So here we have a single slit. When light reaches here, let's have a wall, we end up having, so light that goes from the top and hits here, creates a bright spot. And if we look here, so if I look right here, so remember that it's a transverse wave. So right here, we have a trough. And here we have a crest. So we will get deconstructive interference because this path is longer than that path. So if we have, or let me do it right here. So if we have two different ways to get here, so waves coming from the bottom, these two waves are a different length. We can also have, let's say that we have a thin film. So thin film interference. So let's say that we have a very thin film of a liquid that's only a few atoms thick. about the thickness of a wavelength. So light can come in, strike the surface, and get reflected. Light could also come down here, strike this, so it could pass through the film, strike this surface, and get reflected. This path, because it's taking this additional path, it could be shifted over by half a wavelength, causing it to be a crest here and a trough here when they strike a surface. And it cancels out the constructive interference. So let's look at some examples. So you end up getting these bright and dark bands. That looks more like it. So as it goes through two slits, you get these dark and bright bands. This is a double slit. This is what a single slit versus a double slit. You can see that you can clearly see different things here. You're also getting a combination of single slit in this one too. So you've probably seen thin film interference. Have any of y'all seen gasoline spill out on the sidewalk? What does it look like? So thin. So what's happening is the gasoline is forming a layer that is only a few molecules thick. And we see areas where all the red colors have interfered and been removed, and it just looks blue. We see areas where most of the blue has interfered and all we can see is red. So this is also areas where constructive interference for blue adds up and we see very bright blue. This also works on bubbles. So a bubble is very thin on the level of just a few molecules of soap or water. And we can see that here, blue light is being more constructively interfered, meaning getting brighter, while other colors are being faded away. Or we can see here, red is being more brightened, while blue is being reduced. And this is due to the fact that the wavelength, or that the light is being both reflected at the same time it's being able to pass through and reflecting on the other. So light is able to one spot reflect, the other spot passes through and reflects on the second boundary. And we can see the crest and trough interfering, and so that color of light doesn't work, or it cancels each other out. I have something known as a diffraction grating. So instead of two slits, it has multiple slits like this. So this is a slit that allows light to pass through. And then I have an area like this. And if I were to shine a laser through it, you're going to see regions that are, so again, it's just material. You can actually see some diffraction going on. Look through the paper. So I have a laser that emits 532 nanometer light. I have a diffraction grading that has the split, I think, 40 micrometers apart. And we get that deconstructive interference happens in this region, and light disappears. We also get, because it's going through a tiny little slit, the light is going to spread out. And in these regions, we get constructive interference and light. You also see how it's hazy as it is trying to spread out. But in these regions, we get where all of the threats merge and begin a light laser. This literally has tiny little slits, little holes in it. If you shine it through just normal glasses. So again, laser. And if I do it through this, I get then I can stop some pattern. Yes, we're done. Y'all have like 3 minutes of class left. Have y'all turned in the homework?